After you have your first look at square roots, the next thing you need to learn how to do is simplify them. Now, some of the simplifications are going to be very obvious as what needs to be done. For example, if you had written square root of 36, you wouldn't want to leave it like that. Just like you wouldn't leave an answer 3 times 5, you'd go ahead and multiply and call it 15. With the square root of 36, since it is a perfect square, we want to go ahead and take its square root. So I guess the first rule is, if it's a perfect square, take its square root. Another example of the same thing, if I had the square root of a 121x to the second, I'd want to go ahead and take its square root because it is a perfect square. Square root of 121 is 11, and the square root of x squared is x. Now this again is where it is very important to be able to recognize your perfect squares. Numbers like 9, 16, 25, 81, those are perfect squares, but certain variables are perfect squares as well. And it wouldn't hurt us to take a look at what some of those are. If I took x and squared it, I would get x squared, so there's a first and very obvious perfect square. If I took x squared and squared it, I would get x to the fourth. If I took x cubed and squared it, I would get x to the sixth. If I took x to the fourth and squared it, I would get x to the eighth, etc. So basically what we're seeing here is that any time the variable has an even exponent sitting upon it, it's a perfect square. So, like we said, our first rule, if it's a perfect square, take its square root. Now the next rule is, what do we do when we're dealing with a number that isn't a perfect square? Like 18 is definitely not on our list of perfect squares. Well, it may not be simplified if it contains a perfect square. And by containing a perfect square, we mean that the 18 can be broken up into 9 times 2. So even though 18 itself isn't a perfect square, it contains one when you factor it. Now we have a rule that will allow us to simplify this. And we have a rule that says the square root of a times b is equal to the square root of a times the square root of b when both a and b are greater than or equal to 0. And basically you can read that to mean when they aren't negative values. So since the 18 can be broken up into the 9 times 2, this rule says that this can be further broken up into the square root of 9 times the square root of 2. The square root of 9 can be calculated, so we need to do it. And 2 is not a perfect square. It doesn't contain any perfect squares, so that's where we can stop. Let's take another look at a problem like this. Let's look at the square root of 12. 12 is not a perfect square, so we won't try and take its square root. But like the last example, it contains one. 12 can be broken up into 4 times 3. Our product rule says that that can be further broken into the square root of 4 times the square root of 3. 4 is a perfect square, so I will take its square root. 3 isn't, and it doesn't contain any, so that's the way you will leave it. Now, with some of these examples, the numbers are small enough to where it's easy to see what perfect square is contained. For example, square root of 75. It's starting to get to be a larger number, but I think we should still be able to see, if you familiarize yourself with your list of perfect squares, the 75 can be broken down to a 25 times 3, which again, according to the same rule, can be broken down into the square root of 25 times the square root of 3. Square root of 25, you know that that's a 5, and square root of 3 remains square root of 3 because you can't take it to perfect square. Now, the next example we need to look at is what happens when the number gets a little bit larger And it's not so easy to tell what the perfect square is that is within it. For example, square root of 80. Let's say that you don't know what perfect square that contains. And even if you do know a perfect square that it contains, maybe you don't know the biggest one. Let's see what we can do. We can come off to the side and look at a factor tree. You take the 80 and basically break it down just any way you can. I think an obvious one is 8 times 10. And then you go on breaking it down even further until you start seeing perfect squares. 8 can be broken down into a 4 times a 2. 10 can be broken down into a 2 times a 5. Now we're seeing perfect squares here in more than one way. First of all, 4 itself is a perfect square. And since we have a pair of 2's right here, if they were multiplied back together, they would form a perfect square, since there's 2 of them. So basically what I do is I multiply all of this back out. 4 times 2 is 8, times 2 again is 16, and multiplying it all back out shows you what the largest perfect square is that could possibly be pulled out. So we're seeing that the 80 needs to be broken into 16 times 5 if you want to see your largest perfect square. And the next step, the one I was performing on this last page, the rule says we can do it, doesn't say we have to. So to save time, what you can start doing is saying the square root of 16 is 4, and the square root of 5 has to stay in. So in other words, you don't have to actually show that step every single time. Let's look at another numerical value. Let's look at the square root of a 180. Again, a fairly large value. You may think you know what the biggest perfect square is that's in there, but let's pull it apart and see. I think an obvious factorization is an 18 times a 10, which is a 9 times 2 times a 2 times a 5. So again we see here's one perfect square, there's another. Multiply out 9 times 2, which is 18, times 2, which is a 36. So 36 times 5 is the way you will break that down. Square root of 36 is 6, that comes out. Square root of 5 you can't do, so it stays in. Alright, let's look at one more example of that. And again, look at even a larger number. Let's look at the square root of 243. And just looking at that, I definitely can't tell what the largest perfect square is going to be in there. So I'll start breaking it apart. Now, 243, I believe that can be divided by 3. Let's see what we get out of that. Let's take 243, divide it by 3, and we're going to get an 81. So 3 times 81, and there's our biggest perfect square, because 3 doesn't contain any perfect squares. Square root of 81 is 9, and then there's the square root of 3. So with the constants, that's easy enough. Let's look and see how it works with the variables. Now remember, an even power means your variable is a perfect square. So what about the odd powers? What do we do? What about the square root of x to the 13th power? Well, to find the largest perfect square there, we're always going to drop the power by 1. In other words, dropping it by 1 means break it into an x to the 12th times an x to the 1st. In other words, with any odd number, if you drop down by 1, you've hit an even. So, it's going to, what plus what gives you 12? Well, x to the 6th. And x to the 6th will give you 12. So that's why the square root is x to the 6th. Alright, let's look at another one. Let's look at the square root of x to the 17th, y to the 14th. How do I break that down? The 17th power will break down to a 16th and a 1st. And the 14th doesn't need to break down at all. It's already even. 16th power, you take its square root and you get an 8th. Because what you can actually do is take 16th power divided by second root, and that'll show you the 8th. There's your x to the first staying in. 14 divided by 2 is a y to the 7th. And actually what that brings us to is a very interesting little trick that you can use. Works with not just square roots, but any root. You can actually take the power on the variable and divide it by the root and see what the result's going to be just based on that. In other words, if I had an a to the 7th, b to the 6th, c to the 11th, I could say, and again write down the 2 that's just imagined. 2 goes into 7 3 times, so a to the third comes out with a remainder of 1. 1 remains in. 6 divided by 2 goes 3 times with no remainder. 11 divided by 2 goes 5 times with a 1 remainder. So that's an easy trick that you can use to figure out what comes out and what stays in. Now we can combine what we've been doing here and simplify expressions that contain both constants and variables. We've had the square root of 108 a square b to the 9th and c to the 17th. I'd first work with the constant. So I'm going to take the 108, like I was doing, and break it apart. Let's see, I believe it can be divided by 3. Let's see if that's true. 108 divided by 3 is going to give us a 36, so that was a good way to break that up. So this is going to become the square root of a 36 times 3. And then there's your a squared, b to the 9th, c to the 17th. So, square root of 36 is 6, and a 3 stays in. Square root of a squared is a. Square root of b to the 9, let's see what happens. 9 divided by 2 goes 4 times, with 1 left in. 17 divided by 2 goes 8 times, with 1 left in. So there's a couple examples of how we can simplify these roots. And we're using the property. Again, remember the property says that multiplication can be broken apart. It's actually true that multiplication that's already been broken apart can be put back together. A good example of this is if we had the square root of 60 times the square root of 5, we could go ahead and just multiply those back together. 60 times 5 is 300. So once it's been put back together, we can go looking for perfect squares. Let's see, that's a 30 times a 10, which is 3 times 10 times, oh, look, there's our perfect square. So we should break this apart into a 100 times 3, 10 square roots of 3. So if it's given to you already broken apart, it's usually best to put it back together and then start looking for your perfect squares at that point.